So, as I said, I'll provide an overview of the first Clarity Enhancement Challenge, and then I'll pass it on over to Jon, who will talk about the results of the first challenge. Some of this material you may have heard a little about yesterday, so forgive me if it's not new. So in the Clarity project, the machine learning approach is applied to the problem of hearing aid processing of speech and noise, where current technology in enhancing the speech signal for the hearing aid wearer is sometimes ineffective. Hearing aid manufacturers often say that their products help wearers to hear speech more clearly. However, there have been studies of hearing aid wearers that have found that difficulty hearing speech is the most common reason for discontinued use of hearing aids. Other common reasons include that hearing aids do not help and that noisy situations are too disturbing. And when hearing aids fail, people often withdraw from social contact and their well-being suffers, as Carolina mentioned yesterday. Our project aims to use machine learning to make speech and noise processed by hearing aids more intelligible. And as Jon mentioned, we can harness recent advances in machine learning and apply them to hearing aids. So why use machine learning to solve this problem? Over the last few decades, there have been major and rapid advances in machine learning applied to speech technology, for example, in automatic speech recognition. And this is in part due to public competitions. We want to apply the same approach to hearing aid processing of speech and noise. To this end, we are running interleaved enhancement and prediction challenges, where the objective of the enhancement challenges is to develop hearing aid signal processing algorithms that improve speech intelligibility, while the objective of the prediction challenges is to predict the intelligibility of speech processed by hearing aids. In the scenario for the first round, the listener and talker are in a living room, simulated living room, and there is background noise from a domestic noise appliance or a TV or radio. And this scenario was informed by focus group findings. In the enhancement challenges, participants are given speech and noise stimuli and listener pairings and generative tools to create all of the input signals to the hearing aid processor. The participants submit their processed speech to be evaluated, and the intelligibility of their signals is evaluated initially by means of an objective intelligibility metric, as Jon mentioned, and then by means of listening tests. We're calling the first enhancement challenge CEC1 for convenience. In round one of the challenges, we provide open source code for generating hearing aid input signals for each scene. As you can see in the diagram, the scene generator takes the metadata for the scene, and according to that metadata, chooses the input target speech and noise signals, convolves them with the room impulse responses, shown here as the geometric room model, and the head-related impulse responses, shown here as the measured head-related transfer functions database. The tool then scales the noise signals to obtain the correct mixture SNR and outputs the speech and noise mixture signals. For those who weren't able to attend our presentation yesterday, it's worth repeating that in the first enhancement challenge, CEC1, we provide the following data: the training data set, which is limited to 6,000 of the 10,000 scenes, the development or validation set, and the evaluation or test set, which is smaller. We also provide scene to listener pairings for the training, development and evaluation data, and listener pure tone audiograms. The evaluation data set only includes the input signals for the 3 microphones of the hearing aid, the listener audiograms, and these scene listener pairings. In round one, we provide an open source baseline system to use as a starting point, if people desire. This comprises a hearing aid processor, a hearing loss model, and a speech intelligibility model. And I'll speak briefly about each of these. So here you can see how the scene generator creates signals that are fed into the rest of the pipeline. Scene generator is the blue block underneath, and we have the mixture signals and the listener metadata entering the pipeline on the left, going through the yellow enhancement block, which involves a fitting prescription in baseline or settings for the hearing aid, and a hearing aid model. And then the orange prediction block, which includes a hearing loss model and a speech intelligibility model, and outcomes a predicted speech intelligibility score for a particular mixture signal and listener. Our enhancement challenge, which we're reporting on today, involves replacing the yellow block in this system, while the later prediction challenge involves replacing the orange block in this system. And my colleague Trevor will speak about this later. The baseline hearing aid processor is based on the Open Master Hearing Aid, or Open MHA, and in this case it simulates a basic behind the ear model, front, middle and rear microphones. There is no connection between the two ears, so this is not a true binaural hearing aid, and we aren't modelling the tubal ear mold or considering the direct path or microphone sense noise or feedback in this round. Our Python code creates the input signals from the front and rear microphone signals and a configuration file for a given set of audiograms. And it runs OpenMHA with the configuration file and input signal. The gain table for our multiband dynamic compression component is calculated according to the CamFit compressor prescription, which is an early version of CamEQ. As I mentioned, our baseline hearing aid is designed to be a basic model which does multiband dynamic compression. It also attenuates noise coming from the rear hemisphere. We didn't want to implement any proprietary software components which can't be replicated, such as true binaural processing. Our hearing loss model is a Python implementation of a model developed by Brian Moore, Michael Stone and colleagues at the University of Cambridge, which simulates the main aspects of sensory neural hearing loss. That is the raising of auditory thresholds, loudness recruitment, and impaired frequency selectivity and temporal resolution. The baseline speech intelligibility model is a binaural version of the short time objective intelligibility metric termed MBSTOI, which is what is called an intrusive metric, which requires access to a clean target speech signal. MBSTOI is a correlation-based model that can estimate the effects of nonlinear processing on intelligibility, such as any clipping performed by the hearing aid, and which doesn't require that degradation be in the form of additive noise or reverberation like some early speech intelligibility metrics. MBSTOI includes an equalization cancellation stage and a better ear stage to model the advantage of having two ears. It may be worth mentioning that some drawbacks of this model in the current context are that it is level independent and that it is not robust to frequency shifting. I'll now pass over to Jon, who will present the results of the first enhancement challenge.
Thank you, Simone. Hopefully people can now see my screen. There should be a slide saying Clarity Enhancement Challenge entries and results.
That's all working, Jon.
Good, thank you. So yeah, thank you, Simone, for presenting the challenge infrastructure. I can now go and talk a bit about the entries we had and some initial conclusions and results. After this, there'll be individual talks from the teams themselves who will go into a lot more detail about how their systems were constructed. So we had 14 teams pre-registered to submit systems. This ended up resulting in 8 systems being submitted after kind of 6 late withdrawals. Because of problems with COVID and delays to things getting started, I think it was really difficult for teams to actually get this work done and meet our deadlines. So we're very pleased actually that 14 teams were engaged. The teams that withdrew, some were simply because they weren't able to get things finished on time, a couple because they weren't kind of satisfied with their system performance. But after that, we've had 8 systems submitted, which means 9 systems including the baseline. Each of the teams submitted a technical paper to describe what they had done. And these were reviewed by our scientific committee to check with compliance around the rules of the competition. So these rules are around the use of the data and in particular, latency rules that we stipulated for the processing. So it was decided that all submissions actually complied with the rules. So that gave us 9 systems that could go forward to the listening tests. 9 was a bit of an awkward number for the listening tests because of the way our panel is constructed. It was nice to have 10. So we've actually invited one team to submit a second entry based on the paper they submitted, which had 2 different versions of their system, which actually addressed quite a nice scientific question. So we ended up with 10 systems going forward to listening tests. So in the evaluation, there's MBSTOI evaluation, the objective measure, and listening test evaluation. We actually allowed teams to submit 2 entries, one optimized for MBSTOI and one optimized for listening tests. The point here was that although we're pushing the MBSTOI in the first round as this kind of objective measure, which should lead to good listening test results, of course, we don't know that. And part of the point of these challenges is to develop better objective measures. So if you were a machine learning group and you were just doing what you were told to do and optimize MBSTOI, that isn't necessarily going to guarantee you do well in listening tests, but we still wanted to reward people who'd got those good results in MBSTOI. At the same time, people who know how to make kind of good hearing aid algorithms shouldn't be penalized for doing badly in MBSTOI if MBSTOI is not a great metric. So basically, we have 2 sets of prizes and two rankings. As it happens, only 3 teams took advantage of being allowed to submit 2 versions of the systems. So that led to 13 systems being evaluated for MBSTOI. Where we did have 2 entries, we evaluated both entries in MBSTOI anyway, so that we could get a direct comparison between MBSTOI scores and listening test scores for the listening test system. So we've got essentially 13 teams in the MBSTOI evaluation and 10 in the listening tests. So how do these systems work? So we did a little bit of analysis looking through the papers and trying to see kind of the techniques that people used. I'm going to give a very brief overview of that. So apologies if I've kind of oversimplified your system or misrepresented it, but this is just an overview so people can see generally kind of how the systems are working. All these systems basically have up to 3 components. There's some possible kind of classical beamforming component. There's some DNN noise removal component, and then there's some sort of hearing loss compensation. For the beamforming, we've had about half the teams actually decided to use a kind of classical beamforming algorithm. We've got recursive least squares, we've got minimum variance distortionless response, and we've got linearly constrained minimum variance beamformers. So these are all adaptive beamformers that may or may not be used in the front end. Then for the DNN noise removal, there's again a mixture of techniques. Interestingly, some systems were deciding not to use any kind of DNN noise removal. Others have done. Those that have done, convolutional TASNet was a very common approach. So this is a kind of end-to-end kind of encoder, masking, decoder architecture. So there's convolutional TASNet, and then there's kind of multi-channel variants of convolutional TASNet. One quite interesting kind of binaural convolutional TASNet with different binaural chains with a kind of intentional layer between. We've also had people using 2D convolutional neural networks. Some people have explicit WP for dereverberation. Sometimes the dereverberation has been done in the beamforming, so the rated LCMP is actually doing dereverberation as well. And then on the hearing loss compensation, again, a mixture of approaches. Some people using quite simple linear gains with a very kind of fixed fitting formula. Other people have used linear gains, but have actually tried to optimize the fitting formula using a kind of neural network to optimize it to maximize MBSTOI. Other people are using multi-band dynamic range compression, so kind of nonlinear fittings. So this, you can see across the 13 systems here, quite a lot of diversity, which is really nice actually for our kind of scientific findings of our challenge. It'd be a shame if all these systems are the same. So MBSTOI evaluation. So here we see MBSTOI scores. I've divided them into MBSTOI scores for the speech signals, so that's speech and speech, and the speech and noise. But then we ranked them by the kind of overall average of these two. And here are the team entry numbers. I'm not at this stage going to reveal any team identities. We're only going to talk about team entry numbers. When we come to awarding prizes, we'll reveal the top 3 teams. If people wish to identify their team entry numbers in their talks, they're willing to do so. So this is actually the baseline system down here on the far right, so which is nice. EO1 with an MBSTOI score of around 0.3. So as it turns out, every entry is getting significantly above the baseline. In some ways, it's probably not surprising. I think teams that weren't doing better than the baseline in development set might have decided not to submit, and that might be why we had quite a few kind of late withdrawals. What you'll notice is that speech and noise scores for MBSTOI are very highly correlated. Teams doing well in one have done well in the other. If we rank them by the speech score or rank them by the noise score, you'll see the ranking doesn't really change. It makes a small difference to a couple of the systems. So essentially, these systems, in terms of MBSTOI, are doing equally well for both types of signal. What we're going to see actually is that teams that have done well in MBSTOI are not necessarily the same teams that have done well in the listening experiments. And this perhaps isn't surprising. We'll discuss this a bit later. Just as some sort of validation of MBSTOI, we looked at some of the scores of MBSTOI in relation to the scenes. And we found, it is behaving kind of sensibly. If you look at the SNR here, we've got MBSTOI scores, plot average MBSTOI scores for scenes against SNR for noise and speech. And you can see as the SNR increases, the MBSTOI score increases, as you'd imagine. For a given SNR, speech and noise is actually scoring slightly higher than speech and speech. We find MBSTOI decreases as the distance between the target and listener increases, as you'd expect. And it decreases as the average frequency hearing loss increases. So for the listeners with poor hearing, it's harder to get a good MBSTOI score. Also, if you look at individual systems, MBSTOI scores against SNR, you'll see that the ranking stays about, I think, the same across all SNRs. So it's not like some systems are doing really well at low SNRs and better at, or worse at high SNRs. If a system's doing well, it's doing well. And the ranking across SNRs is pretty consistent. So what works? So again, here's our table of systems in the entry number order. If we reorder this in terms of MBSTOI performance, we see this picture here. So what we're seeing here is that at least for getting high MBSTOI scores, the beamforming, in fact, has not been so important. And teams that are doing well, it's not really quite apparent here, but what teams are doing well are kind of optimizing directly for MBSTOI. So often using some sort of system which looks at the MBSTOI output and does a kind of machine learning algorithm to optimize all the parameters in the system to directly try and get the highest score of MBSTOI as possible. And perhaps not surprisingly, that leads to very high MBSTOI scores. But as we'll see later, that doesn't necessarily lead to the best outcomes in the listening tests. I don't think I have anything more that pertinent to say about that slide. So I'll go on to talk about the listening test evaluation results. So first up, unfortunately, I can't, or today we're not going to be able to give a final result here. The listening tests are taking a little bit longer than anticipated. This is mainly due to kind of delays in recruitment, which are partly because audiology clinics not being open during COVID. That slowed us down a lot. We've got the whole set of listeners recruited. They're currently doing listening tests. 1/3 are completely finished. 1/3 are in progress and 1/3 are still just starting really. So the results you're going to see now are provisional results based on the 1/3 that are fully complete. That's 15 listeners. I think with those 15, a clear picture is emerging, but we're not going to announce winners because the ranking might be overturned in the next period. So here is the overall scores. Again, looking at intelligibility scores. So on the left here, sorry, there's no label on the axis, but that is the intelligibility score in terms of correctness, where 100 would mean listeners getting every word right and 0 would mean they're getting every word wrong. And that's averaged over the speech and noise condition and the speech and speech condition. Now, what's interesting in here is that unlike MBSTOI, if we look at this in terms of the noise tests and the speech tests, you'll see that systems don't behave similarly. So what we have is some systems are doing extremely well in the noise tests, but much more poorly in the speech tests. A few systems that seem to be able to do well in both, and systems that do kind of poorly in both. So I want to kind of dig into that a little bit and give some sort of explanation about why that might be. And you'll hear a lot more about this, I'm sure, in the talks that follow from individual entrants. So if you rank by noise, you'll see that the highest scores here are kind of compared to the baseline, which is EEO1 again, where about 30% of the words are being recognized correctly, getting up to about 80%. And this system, EEO3, is the winning system. The difference here between these top systems are small, but they're probably just about going to be significant. Like I'm saying, as further results come in, the rankings may change. But definitely the top 3 systems here are probably the best for speech in noise. For speech and speech, this is the dark blue bar. You'll see, a big spread in performances and some really strange outliers where you've got the EO3 system, which was actually the best in the speech and noise condition, performing the worst in the speech and speech condition. So interesting question, why might this be? If you look at the intelligibility versus MBSTOI, one of the things we want to look at in this challenge is, does MBSTOI predict intelligibility? Here we just got data points for each of the systems. We've got their MBSTOI score along the x-axis and their intelligibility score on the y. And you can see, what you can say is, in order to do an intelligibility test, you've got to be scoring highly in MBSTOI. If you're scoring high and above 0.6, you're going to score well in intelligibility. Amongst that cluster at the top, there isn't much correlation. But poor MBSTOI scores do lead to poor intelligibility scores. But there's kind of quite weak correlation amongst the best systems. So that's so in the noise condition. And in the speech condition, things are all over the place. You'll see some systems with high MBSTOI scores are doing very well. But then you've got some of the very highest MBSTOI scores actually starting to do badly again. So what works for listening tests? So now this looks quite different. So here I've now ranked the systems in terms of their performance again for the speech and noise. And now you can see that all the beamforming systems are actually moving to the top. So having a good classic beamformer is super important for speech and noise. And then you can see noise removal is also relevant here. Where you've got a couple of systems here very similar in terms of they're identical apart from this noise removal component. So second and third place system there, you can see that the noise removal component is providing some small advantage. If you look at this speech and speech performance, things are a little bit more confusing. And what we see here now is that, again, the best systems typically have a beamformer at the front, but the DNN noise removal component can be detrimental. And the top 2 systems here have not done any explicit noise removal. And again, where systems are comparable, when you add in the kind of DNN noise removal, the scores in speech and speech get worse. So what's going on here? Why is this problem in the speech condition? Well, it turns out that this is it's kind of hard to kind of, I think we're going to hear more about this later, but it's kind of hard to kind of characterize this very kind of clearly. But basically, the DNN noise removal subtracts the masker so well, particularly in the period at the beginning of the signal where the listener's only hearing the masker, that the listener's perception of the task now is that 2 voices start at once. So the target will be starting at the same time as the distractor. And the lead-in part where they're meant to hear the distractor only is basically been completely filtered out and is below their thresholds and they do not hear it. This causes a lot of confusion for the listeners. So we're getting responses like, I'm only hearing one voice, which voice I meant to report? I was told I was going to expect 2 voices, but I'm only hearing 1. And even though they know the target voice is meant to start later, it doesn't help them when 2 voices start at once. If you start looking through listeners' responses, we find a mixture. Some listeners are kind of figuring it out and behaving a little bit consistently. Some are kind of throwing their hands up in the air and just responding with nothing, giving up. Some are responding to the masker interferer rather than the target. And this will depend on how well that mask has been filtered out by the system. So there's a lot of interactions here between systems and listeners in this condition. Because of this, we have, when we come to award prizes, decided to, rather than give prizes to first, second, and third, we're going to award separate prizes for the speech and noise condition and for the speech and speech condition. And we'll probably end up with an overall prize and a joint second place for speech and speech and noise. Some very initial and broad conclusions just from observations from looking at these entries. And none of these are very surprising, but they're all kind of worth saying. A good beamform, I think, is very important. But note, in this first challenge, this is a stationary source condition. So we kind of played ourselves into the hands of the beamforming community. If you can estimate where that interferer is coming from, and it's going to be in the same place, it's in some ways much more easy to filter it out than it would be in a real dynamic scene. So that's why it's super important for us to move on to dynamic scenes in round 2. DNN noise removal is very effective, especially in the noise conditions. But in the speech and speech condition, it's causing problems in our listening tests. Now, this could just be because of the way we've constructed our listening tests. But if you start to think about it, actually it's quite hard to construct listening tests for speech and speech in a way that would remove this problem, because as soon as you have situations where the target and interferer are both onsetting at the same time, and maybe as a result of the processing that's onsetting at the same time, things become very confusing, and you have kind of big kind of informational masking problems for listeners. And finally, directly optimizing MBSTOI, although it kind of wins you prizes maybe in the Clarity Challenge, does not necessarily guarantee good listening test results. So, this shows the importance of developing kind of new prediction metrics that we can use in future challenges. So I think at that point,